Oh, yeah. All right, welcome back, everyone. So today we're going to be diving into Chapter 8 of the Forensics Investigator Handbook, and we're going to be talking about network forensics. So up until now, we've focused entirely on host-based artifacts, examining dead hard drives to live media, whether or not we're talking about Windows or forensics or Mac systems. And today we're gonna step off the endpoint and onto the wire itself. Network forensics is the capture, recording, and analysis of network events to discover the source of security attacks. For the exam, you must understand how to intercept data in transit, analyze malicious traffic, and reconstruct exactly what an attacker did over the network. Now, our learning objective for this module is going to cover 4 primary domains. First is going to be traffic analysis. You need to understand the critical differences between capturing live, full data stream packets versus capturing a summary of data flow, otherwise known as net flow. Second is going to be log correlation. We'll discuss how to aggregate and parse evidence from multiple network choke points, including firewalls and intrusion detection systems, routers, and even web proxies. Third is going to be wireless security. You need to have some basic understanding of wireless LAN forensics, the vulnerabilities of WEP and WPA encryption, and how attackers deploy rogue access points. And then finally, we're going to go over attack signatures, focusing on specific types of network attacks like port scans, ARP spoofing, and physically look at the network packet level. So, network evidence sources itself. The famous saying in incident response is, the network never lies. When an attacker breaches a server, the first thing they do is attempt to cover their tracks. They wipe the hard drive, delete event logs, and clear bash history. However, they cannot erase the packets that have already crossed the wire and have been captured by your network infrastructure. Your evidence sources are like your firewalls, which can provide allow and deny logs. IDSs, IPS systems will provide signature-based alerts. DHCP logs, which are absolutely critical because they allow you to map a specific changing of an IP address back to a permanent hardware MAC address at the same exact moment in time. Okay, so when capturing network data, we generally classify it into 3 distinct types, each within its own forensics value and storage requirement. The first one is going to be a full packet capture. These are normally called PCAPs. Okay, this is the CCTV recording. It stores both the packet headers and the actual data packet payload. With a PCAP, you can reconstruct emails, download images, and extract malware files. The downside, it requires a massive amount of storage. Okay, they're expensive and they pose major privacy concerns depending on what data we are trying to log. Second will be session data. This is normally known as the NetFlow data. This is the call log. It's invented by Cisco. NetFlow doesn't record the payload itself, it only records the metadata. Who talked to whom, when, what port, and exactly how many bytes were transferred. It's highly effective, and it's because we're only storing like the call log. So it's efficient for storage and it's excellent for finding data exfiltration. Lastly will be the alert data. This is the alarm bell. Now, this is generated by an IDS or a SIM tool, and this data only exists when specific pre-written signature rules are triggered, like an alert firing for a known malware download or SQL injection attempts. Okay, and so this is all dependent on how well your security team is and how well those rules were written to begin with. To capture this data, we must get our sensor onto the network. For the exam, we need to know the 2 primary ways that we do this. The first way is going to be a span port, and that's our port mirroring. It's a software configuration on a managed switch. You'll tell the switch to say, hey, take a copy of all traffic going through ports 1 and maybe mirror it to port 5. This is where the forensic laptop would be connected. However, if the switch is under heavy load, it will drop mirror packets to save CPU resources, causing you to lose evidence anyway. The other way is going to be the network tap. The network tap itself is a physical hardware device placed in line between two network nodes. It's like a router and a switch. Now, taps are fault tolerant. They don't drop packets under heavy load and are considered the gold standard for forensics evidence collection. Regardless of the method that you capture, your interface must be set into promiscuous mode, allowing your network to read all traffic on the wire and not just this traffic specifically to its own MAC address. Okay. And then let's talk a little bit about the OSI model slide first. So just remember, you do need to know your OSI model when you're taking this exam, all 7 layers, and know what is physically available on it. So if we were dealing with a layer 2 switch, we're only going to be able to get MAC addresses from that switch versus layer 3. Now we're dealing with IPs and VLANs versus layer 4. Now we've got ports and TCP flags, including the full handshake, which is the SYN/X and ACK. And then all the way up to a layer 7, which normally you're only going to get on a full application firewall to get like things like HTML, emails, or even a SIM or an IDS. Okay, these are the things that are going to go that high. All right. Now, all right, so our primary tool is going to be Wireshark. This is the industry standard for as a GUI. It has great ways for deep packet inspection. And what it does is it acts as a microscope and uses color coding for instant identification, such as green for TCP, blue for UDP, black for errors. It's pretty easy to do that. Now, it does have the ability to follow the stream. And this is going to reassemble packets into readable text files like HTML or email, assuming they're not encrypted. And you can also have powerful filters. So let's say there's a ton of traffic on this PCAP. We can then filter things like, well, we only want to know from 192.168.1.5. Allow us to fully focus on a single host. The next tool would be TCP dump. So when you don't have a GUI, you use TCP dump, and it's default in a lot of Linux and Mac environments. This is what we normally would use. It's a command line workhorse. It's great for servers without a GUI or running automated scripts. For example, if we wanted to get all the information, we can sudo TCP dump-i, the interface -w, where do we want to write it? And basically, this is where we're going to get our PCAP. Now, to filter, we can also use things like we do in Wireshark. We can filter them out, like give me only the traffic from the source of 10.0.0.5 and port 80. Now, always filter because capturing full traffic will fill the disk quite fast, okay? And so we have to be very careful not to crash a system because we're trying to capture a network traffic. And so we normally try to filter if we can. Otherwise, we monitor very closely about the size of those files. What we like to do in the industry is we will also then take these PCAP files, pull them off, and then open them up in Wireshark because it gives us the GUI interface as well. So this PCAP file is a standard PCAP, so we can then open it somewhere else. So you need to know the anatomy of a packet. And so just remember that the Ethernet header contains the source and destination addresses, which was going to prove which physical machine sent it on the local LAN. The IP header is also going to have the source and destination IP address. So not only do we have the MAC addresses now, we have the IP addresses, as well as the time to live, right? The TTL, which is going to be used for routing path analysis and geolocation to let us know how many routes it took. And then the TCP header, which also is going to contain things like source and destination ports and all the flags like SYN, ACK, FIN, reset, all the fun flags, okay, which are used to identify the application and the connection state itself. And then also it helps us identify if there's any types of attacks here, because we want to use what we call is the TCP three-way handshake. Every reliable connection starts with a TCP three-way handshake, and anomalies here indicate attacks. So it normally begins with a client saying, "Hey, hello, I want to talk." It sends a SYN packet, and then the server responds with a SYN-ACK, says, "I hear you, let's talk." And then the client finishes saying, "Acknowledged," establishing the connection. Now, there's some other information that gets sent in this TCP three-way handshake, but just knowing that this handshake has to happen, has to occur before, for one, an established link is actually created on the client, and then for two, to know that there is an actual, proper way of communication is here. Because if an attacker is doing this, they're probably going to do something like a SYN flood attack. They're going to send thousands of SYNs, but never send final acknowledgement messages, which for one could either exhaust the server resources or is a predecessor of knowing that we're being port scanned. Now, DDoSes, there we go, a denial of service attack, or DDoS as well, attacks to crash the service or saturate bandwidth. Forensics, it's a sign of an anomalous volume, right? If we see a massive spike in traffic measured in gigabytes per second, we might say, "Hey, we're being denial of service attacked right now." You'll normally see uniformity, meaning thousands of packets with identical sizes and content. And then finally, the source often is either spoofed or even randomized, just trying to either block the active resources on our server, or a lot of times these are used as a way to flood your network logs, so that way the real data theft that's happening is harder to find. We've got ARP spoofing. ARP spoofing is a layer 2 man-in-the-middle attack, otherwise known as an on-path attack. The attacker tells the victim, "Hey, I'm the router," and then tells the router, "Hey, I'm the victim." And then as a result, all traffic flows directly through the attacker's machine. And to detect this, what we normally would watch for on the switch is a duplicate MAC address on the network. And so we need to look for replies for IPs that don't actually ask for them. So if there's not an ARP request and then someone's just automatically just giving out there, we like to call this a gratuitous ARP, basically saying, "Hey, I'm already giving you the information even though you never asked for it." Those are normally signs of someone trying to do ARP spoofing. Now, wireless forensics deals with a unique medium. We're always going to be dealing with wireless waves here because the big thing here is they can go through walls, and the scene of the crime extends wherever the wireless can penetrate to. Now, for encryption, WP is broken and WPA is broken, and then even WPA2 has its own weaknesses, as we all know. Now, WPA2 or WPA3 packets is useless without a pre-shared key, and so we all know that we have to find out what that pre-shared key is. So performing like a dictionary attack or a handshake or a deauth attack on a WPA2 is something that is definitely something we can look for either in a PCAP or in newly found MAC addresses within a network. So you must also look out for rogue access points or evil twin attacks, especially if we're doing incident response within like a coffee shop or something like that. This is where an attacker is going to set up a Wi-Fi point with the same name as a corporate network and pretend to be you. A lot of times this is a way that they become an on-path attack. They pretend to be you and still forward traffic onto the proper access point itself. Now, other types of wireless attack vectors that are common that we need to know about are going to include things like war driving, which is scanning for open networks while moving. And attackers can also use things like deauthentication attacks, which force legitimate users to disconnect from their current router, reconnect automatically, and then we can capture the WPA handshake either for cracking or replay attacks. Additionally, users can use things like MAC spoofing, changing their MAC address to bypass things like access control lists on a router. That's why MAC authentication isn't the best, because I could just MAC spoof and be able to get onto your network. Because remember, wireless traffic is everywhere. So if I just PCAP the wireless traffic of my area, filter it for your SSID, I can then find people that are already able to talk, are authorized to talk on your router. I can act like that person, and then now all of a sudden I'm able to connect to your router. And so that's something that we always have to be careful about with MAC spoofing. Now, we got to look at the big picture a little bit. Because networks generate so much raw data for humans to read, we're going to rely on correlation, okay? Now, how do we do that? We do it in two different ways. We either use syslogging or SIMS. Syslogging is a standard protocol for sending all of our logs to a centralized system. And remember, we're going to find that on UDP port 514. Now, a SIM, on the other hand, is a security information and event management system. We're going to use tools like Elastic or Splunk or QDAR or Waza to ingest these logs, normalize them, and alert on anomalies. Unfortunately, we as human beings miss things a lot, so using AI and other tools as our level 1 defense and critiquing things are things that we do a lot when we're dealing with a SIM system now. Now, when we want to deal with our logs, firewall logs are also going to be our first line of defense. If we want to know who's coming in, a typical log might be like, hey, a file got dropped here on port 22. I'm not going to read the whole thing, but the interpretations here says the firewall blocked a connection attempt from external address trying to SSH into internal server. Cool. Now, the forensics value here is this log shows reconnaissance attempts like port scans, but before an actual breach occurred. And so we can actually put this within our timeline to say, like, this person was already scanning the network, looking for ports to come into the network, and we can keep that into our investigation report. Now, intrusion detection, on the other hand, using Snort, for anyone who's taken my defense classes, has used Snort in the past. Intrusion detection systems like Snort use signatures to find evil patterns in traffic, okay? And for example, a Snort rule might alert on a TCP connection from any external network to a home network on port 21. Basically, they're looking for FTP traffic, and then maybe they'll be looking for things like user root. So they're trying to log into FTP using root, and so the translation of this rule is alert if any external IP address to our internal networks on FTP and send a text message attempting a root login. And so we could easily get alerted on this, but also be aware we could do the same thing in our SIM. So we could put this into a log system in our SIM and create a Snort backend interface that's also going to be looking for this information. And if it detects it within our network, it can also alert us to let us know that this is happening. Now, web server logs are critical network evidence as well. IAS logs are going to be found in the inetpub logs directory, normally in the system drive itself, and it's going to show a lot of information, like kind of like a firewall rule. All right, it's going to have who asked for it, external IP addresses, source IP addresses, URL query, and a whole bunch of information. Apache is going to do pretty much the same thing. Now, Apache is normally going to be found in the Apache directory and access.log. And remember, most web servers out there are Linux-based, so you really need to understand your Linux systems. Now, during an investigation, we're going to be looking for SQL injection patterns like union select or Active Directory or directory traversal attempts like the .. And if we see this, we can easily know that, hey, we're being, someone's looking, someone's attempting these type of attacks. Now, a major challenge today is going dark because most modern traffic is encrypted either by using TLS, hopefully a modern version of TLS. So packet sniffers are only, like Wireshark, are only going to see gibberish, right? We're not going to see any information here. We'll still see the TCP header traffic, but we won't be able to see any data within those packets themselves because they're probably encrypted. So forensic solutions like traffic analysis, where we can't see the content and the metadata, and we may be able to see volume and timing, but we won't be able to see any information within it. So we may have to get those logs either from the system itself or from the client itself, but the network itself is getting harder and harder to see through because more and more data is being encrypted. But we can also use SSL interception, where corporate firewalls will decrypt the traffic at the edge and then inspect it and re-encrypt it. A lot more corporations are doing this mostly to protect themselves for intellectual property theft. And then finally, we can check the endpoint. Remember, like what I said, from the victim's RAM or anything like that. Now, if we can get that information, we can do a reconstruction process. Reconstruction is the process of turning packets back into files. Remember, we talked about that a little bit with the PCAP. We can do that. So like Network Miner can extract files like images or exes directly from a keycap file. We can, follow the stream and do some kind of reconstruction. But remember, if it's encrypted, we won't be able to do that. And then for VoIP, we can actually replay captured RTP packets and actually listen to the voice encryptions. Now, RTP again is another one of those protocols that it's very rare to find them not encrypted. You're probably going to find an encrypted stream there as well. So we need to know a couple of the tools for this course. You need to be familiar with Wireshark and know that it's used for packet analysis and protocol decoding. We need to know that TCP dump and WinDump handle command line captures. We know that Network Miner is a passive network scanner and can also do artifact extraction, such as instead of doing that follow stream, it can actually extract downloaded files straight from a PCAP, which is really cool. Snort is a IDS and IPS used for signature matching. And then lastly, Splunk is a SIEM, right? And so we have to know at least these ones, but more if we can. And so that was chapter 8, I believe. Sorry. And so to summarize this, we learned that networks can be also another gold mine for our traffic. So we will use taps or spanning ports. Keep in mind that we need promiscuous mode as mandatory for visibility. It doesn't matter if we're dealing with wired or wireless on that. We need promiscuous mode. We're also going to analyze using tools like Wireshark or NetFlow. Remember, there's a difference between having a full network capture and a summarized network capture. We're going to look at different protocols and knowing that we do need a TCP handshake before traffic can flow, and know that how do attackers try to get around this, right? How do we know that we're being network scanned without a full TCP handshake by using like a SYNF flow, or how do we know of ARP requests that are maybe man-in-the-middle ARP requests as ARP spoofing is happening? And then finally, we know, hey, logs are key. Know that TCP port of 514 is going to be a very good port because we need to know that for syslogging. So if you see that 514 is on a server, it probably has a syslog server. So where are those logs going and where are they being correlated? All right, so that is the end of chapter 8. If you have any questions, let me know. Otherwise, I will see you for the next chapter of chapter 9 about doing web and application attacks and how do we search for forensic evidence within those. See you for chapter 9.